Hello community, so great that you are back. Today I have a little bit of an AI revolution for you. So at first, welcome to my channel Discover AI. We have a look at the latest AI research paper, the latest 3 research paper that I selected here for this particular video. And I will talk about a dual-manifold cognitive architecture, and I think this is a little bit of an AI revolution, and I will argue that this might be even the future of the complete AI industry. Let's have a look. Now you know what is the problem. Our LLMs operate currently on a single manifold hypothesis. They flatten all the training data, all the personal habit, all the individual bias, all the historic facts, and all the collective reasoning of a domain like physics or chemistry into a single high-dimensional probability distribution. And up until now, this was just perfect. It was great. But I'm going to argue that our DMCA, our dual-manifold cognitive architecture, will define intelligence much better, not as a next token prediction like we have currently with our LLMs, but as a geometric intersection of 2 distinct topological vector spaces that we are going to build. Now have a look at this. I'm just amazed what here Gemini 3 Pro image preview, my little Nano Banana Pro can do. And I spent about 20 minutes to describe this image here to Nano Banana Pro, and after 3 times we got this beautiful thing. We're gonna go through each and everything, so let's start. This is our paper of today. This is here by Tsinghua University in China, and November 21st, 2025, MirrorMind. And the title tells it all. We want here more or less to mirror a real human mind. We want really to understand a certain scientific personality. Empowering the OmniScientist, the AI scientist, with the expert perspective and the collective knowledge of human scientists. So we're not satisfied anymore to build a synthetic AI system, but we want to bring it closer to the human scientist. You immediately see that we have a common topic, the AI persona agents. Like in one of my last videos, I showed you here the contextual instantiation here of AI persona agents, like shown by the Stanford University just some days ago. And now we have here the other outstanding university, Tsinghua University, and they have now the same topic. And they tell us, when asked to act as a scientist, and you have your prompt here to your eye, hey, act as a financial broker, act as a medical expert, act as a scientist. A standard LLM up until now relies now on a flattened representation of all the textual patterns. But you know what? It lacks here the complete structural memory of a specific individual cognitive trajectory. And this is what Tsinghua University is trying to map now to an advanced AI system. So what they do, they shift here the paradigm from a pure role-playing, you are now a medical expert, which is more or less fragile because you have no idea about the pre-training data for this particular LLM, to a cognitive simulation, which is structured and constrained. I'm going to explain why we have structure and what are the mathematical formulas for the constraint we're going to impose on a specific LLM. Now, the authors of MirrorMind argue now that the scientific discovery is not just fact retrieval. So you see, we go here to a very specific case, we go into science, and we want to have here a discovery process. We want to find new pattern, new interdisciplinary pattern between physics, mathematics, chemistry, pharmacology, whatever. So it is about simulating now the specific cognitive style of a scientist, more or less the individual memory of a human that is now constrained by the field norms. This means by the collective memory. And I think this is really the end of one-size-fits-all agent, yeah? Because all this more or less flat generalist framework like Liang, React, or AutoGen, they all fail in specialized domain, and I have multiple videos on this. But now we're going to build not just a digital twin, but a cognitive digital twin. So they really push the boundaries here for, or let's say, from simple data repos to a functional cognitive model that can predict future AI directions, offering here, and this is now the interesting part, a blueprint for an automatic scientific discovery, and it's not going to be that simple as we have read here in the last publications. So I said, let's start here with our little tiny AI revolution and let's have a look. Now, Tsinghua tells us, so we have here now the individual level, the singular human level. Now we look at the memory structure. And they decide everything that we had up until now was not enough. So they go now with an episodic layer of memory, with a semantic layer of memory, and a persona layer. And one layer builds upon the other, and then we build a gravity well. We build here a force field, if you want, with very specific features. And this is then our first manifold for our dual manifold braining. So let's have a look. They start and they say, okay, the basic is here the episodic memory, no? All the raw papers, all the facts, everything that you have, the PDF, I don't know, the latest 1,000 medical PDFs or the latest 10,000 publication in theoretical physics. Then we go for a semantic memory. But we do have if you want, evolving narrative that is now developing of a single person of the author's research trajectory. Now, if we go for an individual level, we restrict this here to one person, and we just look at the temporal distillation pipeline of this single person. What has the author written in the first month? What has the author written in the second month? And then we go through all the 12 months. We have yearly summaries here, and we want to answer how did the thinking evolve of a single scientist, not just what he has published. So whenever you now give here an LLM or an AI system that has computer use access to your files on your local desktop, laptop, whatever you have, now this is great because now all those data become available. Every email, every file that you worked on, if you prepared your PhD or you prepared any publication, how many months have you been working on this? How many versions of the final paper are stored in your directories? Now, if an AI would have access to this, it would be really able to map your personal or my personal thinking process, my mental, if you want, evolvement here, how I understand this topic. And if we are able to bring this here into a temporal pipeline, we can distill further insights. And then if you have this information, let's say of my persona, we have now an agent or an LLM that can build now my persona schema with all my knowledge about mathematics, theoretical physics, whatever. So we can build now an abstraction, a dynamic concept network, capturing now my, let's say also stylistic, but also my reasoning preferences. All my knowledge is now mapped to an AI system. Plus, we have everything timeline stamped. So we have here, as you see here in the semantic layer, perfect time series going on for months or even years, depending how much data you have on your computer. So they say, okay, let's start with the individual person and let's build this. So let's do this. Let's follow their traces. Okay. The episodic memory, you see this is here the very last layer at the bottom. What is it? We have now what they call a dual index structure to handle here the specificity of the scientific terminology. Now, I don't know about you, but in theoretical physics, we have real long technical terms. Also in astrophysics, long technical terms. In high energy physics, elementary particle physics, long technical terms. Think about medicine, long Latin terms. Think about pharmacology. You understand immediately. You are not allowed to make one single type mistake. So you cannot give this to an LLM. So what do? You build a hybrid RAG engine. No? Of course, our good old friend, the RAG machine. But now the RAG documents are parsed into semantically coherent chunks. So what we do now is we have a certain chunk, let's say a sentence or maybe even a complete paragraph. It's a very homogeneous paragraph. Then we have the source document. This is in file number whatever and we have a timestamp. So exactly here, the recording, when did I write down this sentence on my computer, or when did I publish it, or when did I discuss it, when send it out in an email to my friends. Exactly timestamp and here the complexity of a topic. Now, if you do this for millions and millions and millions of chunk IDs, you get now an idea where we are. And MirrorMind, the authors say, you know what, we looked here at all the vector search capabilities, and they are often too fuzzy for real science. And so what we have to do, we have specific acronyms or chemical formulas. No? They all must be exact. You can't go with an LLM that just has a probability distribution here for the next token prediction. No? So therefore, we will choose not an LLM, but something different. So now they went with the episodic memory that stores every chunk of information they found, let's say on my computer here, in 2 parallel searchable indexes. And the first is a dense vector index. This is what you know. This is a high-dimensional embedding via here the encoder model of a transformer for the conceptual similarities. So we build a new mathematical vector space and we say, okay, given now the semantic similarity of my, let's say, 100 files and the content of these files, we can now place the vectors here in a new vector space, and we can arrange those vectors that we do have conceptual similarity of the technical terms. But talking about technical terms, we now store them separately because we say, we use now a sparse inverted index, so this is a standard BM25 index for an underline exact lexical matching. So we have absolute, the keywords, the symbols, the technical term that we have, and they go in a separate index, so there's no mixing up and there's no hallucination by any LLM. We cannot afford this in physics or chemistry or medicine. And then, since we have now 2 specific scientific indexes, we can merge the result via a rank fusion, a reciprocal rank fusion. And this is the way they set up here the episodic memory of a single researcher. So this is here all the scientific content over the last 5 years that I have here, let's say on my laptop. Great. The next step is here the semantic layer, as you can see. Now the semantic memory builds on the episodic layer and performs what they call now a cognitive distillation. If you are familiar with MapReduce from the very early days of AI, you know exactly what we are looking at. MapReduce, distill, pipeline. This is all there is. So let's say, they use here any LLM to transform them. No? Now all the definitions from the episodic layer come up, and now, just give you an example, I say analyze the cognitive evolution. Focus on any maturation of ideas of this stupid human, any conceptual shift that you can detect here on all the 100,000 files on his notebook, or any changes in the research focus of this person or the methodology he uses, or why suddenly in, I don't know, April 19, I decided to go from a particular branch of mathematics to a more complex branch of mathematics because the complexity of my problems suddenly increase. An LLM should now distill from all the episodic layer elements with the timestamp here, as you see here, the MapReduce pipeline. And if we have this information, you know what we're going to build. We're going to build a trajectory. As you see here, we have a trajectory of time, of trends, of keywords, topics here, whatever. Clusters, you can define your clusters if you're particularly looking for some quantum field theoretical subtopics here. So you see exactly how my knowledge evolved here over the last 5 years. No? And I have to do nothing. I just give you my laptop and this is it. Now they model a cognitive trajectory. So they say now we distill now the semantics. So the system now understands the reasoning link that I had in my mind between paper A I published, or the file A on my laptop, and the file B. So what it does, it captures now and what they call the cognitive inertia of my intellectual topics. Now this is interesting. You see, we have now a 5-year timeline of my scientific work. We have now in the semantic layer the complete time series. And guess what we do next? Yeah, if you want a very simplified explanation, think of a semantic memory as a biograph AI system. Now, it looks at everything that I published on my computer and says, okay, this fellow, oh no, there's no way he's doing science. No? So turns isolated timestamp into a cohesive intellectual history. And if we have this, now the next step is, of course, and you already guessed it, we have now a mathematical transformation. We have now the next step, and we go to the persona layer. Now, I am modeled in my, what to call this, scientific intellectual development. We are now here transforming this here from a temporal flow from the time series into a topological structure. And the simplest topological structure that we know is here a knowledge graph with specific weights here. So we have here a particular focus on some topics, and I'm going to explain what I mean in a second. The simplest way to explain this is with an example. Let's say the input signal now entering here the persona layer is now, let's say in 2023, the author moved away from here CNNs, convolutional neural networks, and started focusing heavily on graph neural networks. Now you know this is not true because we did this in 2021 to get on this channel, but just to be here on the safe side, it's just an example. Yeah? And we did this for molecular modeling. See my videos from 2021. Okay, great. So what we do now with this? The system now understands, looking here at this sentence that comes up from the semantic layer and says, okay, we have to create some nodes. Now we have to build a topological structure. Let's have here a knowledge graph. So what is new? We have here CNNs, we have here the GNNs, and we have molecular, and we have modeling. So let's build this. Now, particular of interest is, of course, the quality of the nodes. GNNs are not just a subtopic, but it's a major topic. No graph neural network, so it becomes a concept node. Molecules, there are thousands and millions of different molecules, so it becomes a concept node again. So you see, we already introduce here kind of a hierarchical structure in our knowledge graph. And now we have here a certain weighing that we're going to do, because it might decay or lower now the centrality. This is a graph theoretical feature that I explained in one of my videos of the particular node CNN. Because it is stated falsely that in 2023, and it was 2021, that I moved away from CNNs. So currently, the centrality, the importance here on all the subnets here of my graph, CNNs, are somewhere lower in the importance. No, they are not as important right now. They calculate this with the graph centrality measures. And if we have this, and here you see it, here the persona layer, this is now my profile, I have a profile in machine learning, these are my subtopics, I studied, I learned, I published, I wrote code, I did not publish, I just have on my computer, whatever. And then we have something in bioinformatics, the work I have done, then something, whatever other topic you have, how strong are the interlinks, how strong are the edges between these topics. So we build a knowledge graph of my temporal scientific evolution as a scientist. But you are not happy with this, no? Because we are gonna map this further. So in this step, we mapped it from the temporal flow of the semantic layer of the time series into a topological structure. But this topological structure is not really what we can have a smooth transition and integrals. No, this is a graph. Come on, this is bulky. This is not elegant. No, so what we're going to build is a gravity well. We're going to build a field representation. No? This is here the blue heat map that you see on top. And this shifts now the center, let's say somewhere there was GNN, now shifts here the center here to GNNs. So you see, we have a lot of mapping here to have here the internal individual, let's say my personal evolution. But this is not all done by the AI. No? So now the AI says, okay, let's do some inference. No? So it looks now at the new topology of the graph and asks, given this new shape, what kind of scientist is this person now? If, I don't know, some AI says, okay, who is this person that does here all these beautiful YouTube videos? What is now his actual current characteristics? And now the system might update here, if it's working now for me, the system prompt in a way that it says now him, okay, listen, if you work with this guy as an AI, your style has to be highly theoretical, based on first principle reasoning. So you see, all of this just to arrive at these simple sentences that the AI has now a perfect characteristic of my actual learning experience, understanding what I know, what I do not know, and now the AI is the perfect intellectual sparring partner for me. Now this AI system is the perfect professional AI companion for theoretical physics or bioinformatics or whatever. So what we have achieved is not only build me as a perfect mirror mind for the AI to understand, but the AI can now decide to find the perfect complement to my intellectual morphism So it is the perfect partner for me to have here an augmentation here of an acceleration of the research. Now you can look at this, of course, from a mathematical point of view and say, why was this necessary? I mean, look at this. We went through here 4 different mapping. Why? Well, LLMs cannot calculate a similarity against a story, against my learning. They can calculate it against a vector or a graph state. This is a simple mathematical operation. And now by converting the trajectory into a weighted graph, the system can now mathematically compute, hey, if I get a new idea, how close is this to the current network, to the current, if you want, gravity val here of the, how do you call this, scientific intellectual capacity of this person. Now we can calculate it, and then if we can calculate it, we can code it in Python, C++, whatever you like. Now, I have been already talking here about this gravity val, and I just call it a gravity val, call it whatever you like it, but it's just important that you understand the idea. What is it? And now if we change the framing, if we look at it from a little bit more of a mathematical perspective, you immediately see it's a probability density field that we derived from the topology of the persona graph. No? Persona graph allowed us this mapping here into an n-dimensional gravity well. So how we do this? I mean, how can you have just a stupid graph, a flat planar graph, and suddenly you have a 3-dimensional beauty of a manifold? The authors tell us the way they decided to go. So here they say, okay, first the system calculates the mass of every existing node in our network. And MirrorMind determines here the mass using here a particular graph-specific centrality measure. This is the way they determine now the mass of every node, or if you would say, the importance of, the current temporal evolvement of my scientific knowledge. And then they define also the distance. And the distance, you notice, is of course an embedded space, 1 minus cosine similarity, beautiful. If we go here for an Euclidean simple distance, later we are going to discuss some other hyperbolical spaces, then it becomes a little bit more difficult. Now this blue gravity well is, let's go to the next step of abstraction, a kernel density estimation over the embedding space of the persona graph. Now, I have multiple videos here on this kernel density estimation, but in summary, you can say that the gravity intensity G at a point Q, here in my blue gravity field, and let's say Q is now a new idea, is the sum of the influences of all the nodes in the graph, exponentially decaying with distance. This is the simplest thing you can think of. No? Everything has to contribute to this, but we have an exponential decay function so that not everything is contributing here in equal matters here to this particular, that the points that are the closest are the most influential. Couldn't be easier, no? And here we have this simple formula that the students here or the experts here from Tsinghua University shown us. Great. So what do you do? This deep blue visualizes now the specific region of a, let's call it a latent space, where the authors feels, or I feel, most comfortable. No? You see here in this dark here, I call it more of the same. No? This is my expertise. This is what I know exceptionally well to do. I have worked the last 2 years only on this dark area here in this gravity well. Those are my topics. This is I know well. But of course, if I want to have a brand new discovery, now they argue, maybe it is not exactly in the same old thing that you do for 2 years, because otherwise you would have discovered it. So maybe it is somewhere else. And they say now, okay, so what we have to do now is find a mathematical algorithm, a repulsive force that acts on this, if you want, gravity well structure to bring me out of my minimum over the mountains and somewhere beautiful new. So what I need is a novelty repulsor. I have to have a force acting on me sitting here, boring and doing the same thing over and over again and not discovering anything new. So push me out here of this and let's go somewhere we have never been before. So you see, it wants here to simulate here the discovery, not the repetition. The repetition is done in the blue. And therefore, the algorithm treats here my author persona graph not as a target to hit, but as exactly the negative, as a penalty zone to avoid. Now the things becomes interesting because, yeah, you can push me out with any force out of here my stable position at a minimum, but in what direction do you push me? Where should I go and continue my research on? And now Tsinghua discovers here or says, well, what we have is the second manifold, is an external manifold. And this external manifold is here, let's say here, OpenAlex. So this is the knowledge of all, 1 million published paper in my topics that I research on. It's a free and open source database of scholarly research, paper, author, institution, everything is there. And let's say, okay, this is not the outside world. This is not the second manifold. No? This is here my personal manifold, and this is here the community manifold in total, the global science community. Where they are, what they have done, what they examined, where they failed. And they say, let's do this. And they build now, simple idea, a wireframe grid. So you don't have to build a real smooth manifold. A wireframe grid is enough. You just have some estimation points and you can connect this net in really. Yeah? So what we add here to my stupidity here on the left side in the blue valley here, we add, if you want, a social connection to my social community. This is here the research community from astrophysics. And some new ideas might come from astronomy. Some new idea might come from medicine, whatever. No? So we have now from a simple approach here to an interdisciplinary approach. So we have here now one manifold, the second manifold, and the second manifold is also constructed that we clearly can detect hallucination. Because if the LLM suddenly does some hallucination, we can pocket him here into this rabbit hole and say, okay, let's forget about this hole. What we're interested here is the maximum of the community knowledge. Can I contribute with my knowledge here to the open problem started here at the top of the mountain here, this particular sweet spot? And you see, I told you a force has to push me out, and this is here now the path to optimal research, an optimal research idea P star. As easy as can be. And again, thank you to my Nano Banana Pro, because about 20 minutes it took me that I put all the data in. I said, hey, display the summary. I want this and this positioned over there. And it just did it. There was not one mistake here. Okay. Now, this is now the story. This is my story now as a scientist. But now, of course, we have to code this. So if you want to code this, we have to work with agents. We have to work with LLMs. We have to work with networks. We have to work with different mathematical operations like mapping functions. So let's do this now. Okay, so what we have is, you ought to say, so we need to have a super AI. No, we have an interdisciplinary level where the super coordinator agent is supervising everything. No, this is the mastermind. And this coordinator agent decomposes now an incoming query and routes them to particular domain agents that are navigating here the OpenAlex concept graphs or building the graphs, or the author agents that understand my scientific personality. No? So the system solves now proposing complementary ideas as a dual constraint optimization. I have both manifolds, and in both manifolds I have constraint. And now I have to do a dual constraint optimization process in mathematics. Couldn't be easier, no? It is just the perfect path. Let's do this. So the idea is, or if you want the optimal idea that I'm as a researcher looking for, P star, is forced to exist in the Goldilocks zone, right on the rim. So it has to be valid science that's accepted by the scientific community, but also real close to my particular areas of expertise. So what I'm as an author almost developed, what I almost thought of, but I just didn't do this little tiny baby step. So what we are going for is the easy wins. The AI would analyze, this particular guy here with his YouTube channel, he did some research here and he was almost there to discover something that the community also indicated there might be some new element. So let's tell him, hey, go in this direction, learn this and this and this, and then you will make a significant step in your knowledge and discover a new element. So this is now, and now I need a little bit feedback from my viewers, because I'm now trying to accelerate my learning. But at the same time, I'm trying to accelerate my understanding of a visualization so I can communicate better with you, my viewers, my subscribers, and you, the members of my channel. And this is the first time I really invested heavily into the visuals here with Nano by Nano Pro, for example, to build here a visualization of a complex theorem that is more than 40, 50, 100 papers, and I try to bring it here just on one simple image. It is not easy, but I will try this if you, as my viewer, you like it and you have this additional visualization. So MirrorMind here and the next paper, what we call PersonaAgent, demonstrate now that the vector databases here are simply insufficient for complex reasoning. So what we need more complex graph structure and mapping from graph to graph to represent new and established relations between the different memories. And in MirrorMind, I showed you the temporal evolution of my scientific mind. Now, if you have a closer look at this, especially the semantic memory, it explicitly models how a scientist's mind changes. But you understand what is happening now? We break with one of the most important theorems that we had in artificial intelligence. And this was that everything is a Markovian system. And suddenly, it is not that I just can look at a system and say, this is the current state of the system, and it is not depending on the history. Because now that you mirror a human brain, a human mind, it is very well depending on my personal history, where I started to learn mathematics, then physics, then whatever. And then, bit by bit, I'm a little bit better here. You have to understand here the time evolution. So suddenly we break with a Markovian state. This means that all our algorithms that we have in LLM also break and become invalid, inoperable. So now these things become really interesting. And now you might ask, hey, I'm just here to learn how to code an agent. Do agents do any of those operations you are asking for, you're doing? And I say, so glad that you asked this question. No, because now I can tell you about the multi-agent interaction pattern here in the work done, or the coding here by Tsinghua University. And I want to focus here on the multi-agent cognitive engine. As I told you, we have here an interdisciplinary coordinator here, our super AI that understands everything, can sort everything, can plan everything, can execute everything. Great. So what it does, it gets in here my human query. Hey, I don't know, find me the next research topic, because I'm as a human, I'm too stupid to know where I want to go to. Okay, so this AI says, okay, I send out two query vectors. I send a query vector now to, now I exchanged here the manifold. This is here my human learning manifold on the right side. And on the left side, they send here the same query vector in an embedding here in a mathematical tensor structure now to the other side. And this is here the objective visibility. These are all the 100,000 of research paper that are now suddenly in the brain of an AI system, of course. So this is the collective domain of theoretical physics, of medicine. You get the idea. So let's say we have here built a holographic wireframe wall. So this is my idea. Please go with whatever you like. This is just an illustration I try to find to explain this area to you. And let's say we have here a domain agent. And the domain agent is just reading every day here the latest AI research publication that has to do anything with theoretical physics. And then we have here an agent. This is reading here every single scientific paper that has to do with biology. And they build here their internal representation and their network here, their wireframe here of the complexity of the topics, of the dependencies here in science. Great. So if you want, we have here the domain knowledge graph of physics combined with biology. And now the query vector comes in, and this is a very specific query vector with a brand new idea. And this is now, hey, does the general global research community has ever heard of this idea that I have? How I should develop as a human? Is there anything related to this? Is there any publication that gives me a help? Is there any publication that guides me in my personal development? Anybody has tried something crazy enough or similar enough, and now we're again working with a cosine similarity in a normal vector space. You see, explore the space and says, yeah, we found some path of augmentation that your idea is not as stupid as you think, but maybe it's a valid idea. And we provide now from the complete, if you want, knowledge graph of the world, we provide now the particular output here. This is here the green beam. We provide now as an output. But at the same time, of course, this query vector was sent here to my personal learning manifold. Now, I told you I have a repellent force field here. Now, this is in orange here. But I do not want that if this query vector comes in, it is already the same as I'm already doing. So more of the same. I don't want this. I want to go here for a scientific discovery, go where no one has ever gone before, and you know the story, no? So if this vector here crushes through my force field, it has to have a certain, let's call it impulse, impetus, and then I will analyze this, no? And I just explained to this here all the different layers here of the individual personality of my MirrorMind. And now I discover, is this something, is this an idea that would push me out of my deep blue gravity well into a new direction? And I send out, hey, yeah, this sounds absolutely interesting. This is absolutely novelty. I have my experience in the topic A, B, and C. And now I say, hey, this is my specialization. I have sent out the orange beam, the novelty. So now we have here the knowledge integrator, which is something beautiful. This is now where the braiding is going to happen. We combine now the green beam and the orange beam into something completely new, and the output of this will be my new research direction, my new research title, where I should move to have a scientific discovery as decided by the AI system. Oh, wow. Okay, let's go with this. I hope I'm clear as far as right now. If not, I just want to give you an example. How does it work? Let's say we have the idea, hey, let's build a neuromorphic battery. Now, battery is always a hot topic currently. So how is now the flow diagram? Now, we have a coordinator agent and takes in here my crazy idea, building here a neuromorphic battery. So the coordinator AI say, okay, I activate now an auto agent or already, if I'm already mapped in the AI system, if not, you can build here the auto agent. If you say, hey, build me you get the idea, and a domain agent for biology. Great. So if you want, this is me, and then we have here an agent here for biology. Great. Activates and creates here the agents. Then the auto agent, the individual, if you want, person, builds now or has access to your persona graph, to the history, whatever I have already researched in cathode and electrolytes, in voltage fade, all the constraints here, and do whatever I do every Tuesday, that I build better cathodes. Okay. So I say, don't go there because this is what he is already doing and he was not having any discovery at all. So he pushes me away from those areas that I already do. Then the domain agent, if you want a collective agent here regarding biology, looks now at all the publication, the biology concepts related to energy, finds here neural glia cells, the concept to ion regulation here, returns now, there's something like ion regulation in biology to an electrolyte transport in batteries. Maybe there are some hidden patterns here in the understanding, in the reasoning, in the, molecular transport architecture that we can use now from biology now in battery technology. And then comes here the cooperation phase, here the optimization, as I showed you on the blue well. The coordinator asks, hey, is this a valid path? The domain agent says yes. Mathematically, I showed here, reading here 50,000 publications that we have here. And the auto agent says, hey, I have never mentioned glia cells in my last 50 paper. So this now for me is a complete new topic, but I know everything about the science, no? I just never focused on this particular point of research. So let me do this. And then it scores here a novelty score. And they try to maximize the novelty score, so the AI is now gonna give me a brand new topic. And the integrator now generates here the final output. And the integrator says, after having looked at all the AI research paper and what have you learned in your last 18 years, I give you now a proposal. Design a self-regulating electrolyte gale that mimics an ion buffering capacity of a neural glia cell to prevent voltage spikes. This is your topic. This is your PhD. Do it. If you solve it, you gonna spend or earn millions of dollars. Great. Yeah, you're gonna spend millions of dollars too for AI compute, but never mind about this. So this was the first paper, and I know I told you I want to accelerate my learning. I want to accelerate my explanation, and we can go in higher complexity because now with Nano Banana Pro, hopefully I have a tool to show you my ideas, how I see things, and maybe it becomes clearer to you, or you say, hey buddy, no way what you are thinking. So let's increase here the speed, let's increase here the acceleration, and let's go to another paper. And you see, I place it here, and this is also a paper by November 21st. This is here from Purdue University, Iowa State University, Columbia University, and they have a topic, persona agents with GraphRAG. Our good old friend GraphRAG. So what they build is a community-aware knowledge graph for personalized LLM. And you might think this sounds real similar to what we just did. Well, of course, what a coincidence that I selected this paper. By the way, published on the very same date, no? Okay, they tell us just, is this worth reading? They say, hey, our method improves the categorization here, the F1 score by 11%, and for the movie tagging is now improved by 56%. And I say, okay, if this is the step in the improvement, if we use this, let's have a look at this paper. So, persona agent. So let's say you want to build here a little Einstein. No problem. No? So the authors here tell us, okay, our framework generates personalized prompts now for AI systems by combining here a summary of the user's historical behavior. Let's take again me as a user. So my historical behavior and the preferences extracted from the knowledge graph. So what I'm doing, so if I have multiple AI systems from, I don't know, Anthropic, OpenAI, and Google, and Meta, and Microsoft on my computer, and all of those AI have access to my complete computer and to my complete documentation, everybody has my data. Great. So what they do it, huh? And then we have a mixture, and then we have also the global interaction patterns that we see, let's say, on social media, or all the scientific publication, and who is referencing what other paper. So we have the complete social interaction. Let's go only on the science level. And this can be identified through a graph-based community detection, so social media. We bring it all together. We have the compute power, no problem. No problem at all. Let's go with the complete science community. And let's build here with this user history, who is definitely not an Einstein. How can he become an Einstein? A simple topic, no? So they tell us here, and this is here not my Nano Banana, but this is done here by the authors here. You see here that it's not as beautiful. They say we have a user profile construction. And I already explained everything to you, no? I have a personal preferences, the relevant concept, the interaction statistics of me, all the emails, who I talk to, who I cooperate with, whom I published what paper. And then they have the external knowledge graph construction. So what is happening currently in quantum field theory and theoretical physics, in computational science, all the interaction node, the concept nodes, concepts we already encountered, no? Then they have category, theoretical physics, mathematics, biology, whatever, you know? And then all the semantic relations, remember the cosine similarity in a normalized vector space. So we have the user data and the community data, and then we bring them all together in a mixer, and then we have a personalized agent that is now almost a substitute for this human, but the personalized agent we can develop much faster. No, this will become a machine that is much more intelligent than a human user. This is me, by the way. So what we build a semantic memory and say, hey, I know this. You just talked about this. And I said, yeah, of course. And then we need an episodic memory and say, hey, this was the first layer. Yes, of course. And then we have a community context. And I said, what a surprise. So you see, complete different place at the very same day, they publish something that is almost identical. And they now generate here a personalized prompt that then they feed to the LLM to get a real, highly specialized personalized response. Now the beauty of what they do is they work only with GraphRAG. So they are not going here with BM25 or with some dense algorithm. They are here on the graph level. They are operational only on the graph level. Real nice. So let's go there. So we have now from a graph topology, What we want is the output in a linearized context here for a stupid LLM. If you want, this is here the braiding mechanism that I was already talking about. And here again, what a coincidence. I ask here NanoBanana Pro to generate here almost identical image here for our braiding processor, for our machine that brings here everything together. Okay, let's start. So what we have again, as I told you, we start not with the 3 levels of memory, but we are now operating here in a GraphRAG system. So we have here a graph. And in this graph, I have now interaction node of my history. So that I, the user, read here. Now we are somehow in a movie. So the ghost, and then I watched Matrix. I watched Matrix again, and then I read here a particular book about this. And you see, okay, so these are my interaction nodes. These are here the things. Then they build here what they call here, where is it? The concept nodes. These are the triangulars, no? So this goes to cyberpunk, this goes here to dystopia, this goes here to virtual reality. And you see, we already kind of a hierarchical structure of our node layers. And then we have pure community nodes. So these are the global interaction nodes, no? In general, all the people on this planet liked Ghost in a Shell or whatever metric, Rotten Tomato, whatever you like to use here. So you build here a network. Now this network has, of course, if you want, 2 components. No? So the first component is here my personal stream. Then we have here, how did the community, let's go again with the last 5 years. So how I developed in the last 5 years and how does the research community developed in the last 5 years. And then we have to bring it together in this braiding processor or bipartite fusion operator, whatever you like call it. We're going to have a look in detail what this is doing and how it is doing, but just the idea. And then after we linearize this complexity, we have now, for the LLM context window, we can create a system prompt. We can have a stream A of my personal history and the stream B, where I tell the AI, look, in these 5 years, my sub-community, theoretical physics, developed this and this and this and this. And now this is here the information for you as an LLM. This is my input to you as an LLM. And now you, LLM, do the job. So you see, we are here in the pre-processing of the data to an LLM. So you see that, again, looking here at the graph distribution, we have here the user manifold, and we have, if you want, a community manifold. And now these 2 streams here are brought together. So I'm not, again, squeezing everything into a flat one manifold structure, if it's with a high dimensional, but I separate here very specific persona. This is the blue stream. This is me, for example, or you, to, hey, what is happening in the world? What is happening in the community? If you're an artist, if you're a creative, if you're dance, if you're music, whatever, what is happening in your world? And what you have been doing the last 5 years, and we bring it together and we see what emerges. So this persona agent, and this is here the complete framework here, overcomes now the cognitive flatness that I told you here at the very beginning of this video. How we do this? Through a recursive GraphRAG that we build. So we use something that we know. There's nothing new. It's a little bit new, but everything else is clear. Let's have a look. So what I especially found interesting, how would you code a braiding processor? No, in code. Because what it's doing, it's just a linearization, so it must be real simple, no? And in standard RAG, or retrieval augmented generation, the system retrieves here a list of documents here from external data sources and just pastes them onto one another in the LLM. But this is stacking it, no? This is not braiding. So the LLM often gets confused by contradictory or irrelevant data, because maybe in the data we brought back from RAG is the Earth is flat, and then the Earth is not flat. So what to believe? So let's solve this. Braiding is now a much smarter structural merge operation. It doesn't just pile up the data. So the Earth is flat, the Earth is not flat, the Earth is whatever. It weaves now 2 distinct strands of information together to create a stronger rope. I hope with this image I can communicate what I want to tell you. So the strand A is, of course, the self, so this is my knowledge, and the strand B is the community, the world. No? So strand A more or less is, hey, what have I done the last 5 years in theoretical physics? So this is my personal history. It's not a vector, but yeah, it's a high-dimensional vector, a tensor structure, okay? And strand B is simply, hey, what has everyone else on this planet done and published here on arXiv? No? So this is here the complete knowledge graph, and we have here a traversal vector that we can explore in the simplest case. No? So what is this braiding process? It is, of course, a mathematical function, or if you want an algorithm here, that compares these two strands and finds now an interference pattern. And you say, what? We don't just here add it up? We have a concatenation? No. We have a look now at the interference. So specific points where your unique quirks, my ideas, overlap with the collective trend here of the research community. Very simple example, but it's the simplest example I can think of. Hey, I say the individual stream is, hey, you like dark chocolate, and the collective stream is people who buy red wine also buy dark chocolate, and guess what? The braided output is, yes, you can imagine this. Now, of course, it is a little bit more complicated, and it took me again about 20 minutes that Banana Pro generated this image. I wanted to have it like a Stargate. I don't know if you know this TV series, but exactly. So here we have stream A, here we have stream B, personal, vector, episodic. So with all our little boxes here of knowledge, and then here the collective vector, all the publication that have references to all the other publication, and those reference other publication, and those reference here persona, or this reference here some tweets, or you get the idea. What is happening here? And at first I thought I built it like a DNA strand here, a molecular strand. But no, because what I want this input, and you see here still the DNA strand, it was not eradicated here by Banana Pro, okay? Because this is not the input to our LLM. This is just the data pre-processing for our LLM machine. So I have to bring this to a linearized context tensor that has here a particular optimization routine to have here the perfect input to the LLM. So what is this? Now, if you are a subscriber of my channel, you understand immediately when I tell you, this is nothing else than a graph neural network attention mechanism that we apply at inference time. Okay. So what is happening here? This is the most important area now, this braiding processor with our logic gate, and here every debris that is not as important is just pushed back in space, and we just need here the perfect braided here knowledge stream that enters here the LLM as a linearized tensor structure. Let's do this. Now, if you look at it from a mathematical perspective that I introduced at the beginning of this video, you immediately see that this is a dual source manifold alignment. The first source is here the episodic stream, and the second here is the collective knowledge stream. No? A dual source manifold alignment. So, yeah, followed by gated linearization. Of course, we only have a linear prompt here to our LLM. But of course, it is not a single equation. It would be too easy, come on, This would be not a topic of one of my videos, no? But it is a computational pipeline to project the query into two orthogonal vector spaces. Again. And we have individual and collective. See? Hope this visualization helps, and computes now their intersection to filter out the noise and rank relevance. So let our domain be defined by a heterogeneous knowledge graph on all of theoretical physics. Then we define two distinct submanifolds within this graph structure. Now, you know what it is. It is the individual manifold, so the local subgraph defined here by my little brain, and the collective manifold, the beauty that everybody else on this planet did in the last 5 years doing research, no? And subgraph reachable through a community traversal. And now the task is, the stream A is an individual resonance score that we can calculate, and we call this parameter alpha. So this measures how well a candidate node aligns with the user-established history. It combines the semantic similarity with the historical weights. The stream B is, of course, the collective feasibility score from the whole community. We call this parameter beta. And this measures now how strongly the node is supported by the topology of the domain graph itself. So more or less, is this a valid node? Am I allowed to sync this in my individual vector stream? Is this really something that the community recognized as, yeah, this is something, an object that it would be worth to investigate? Beta computes here the random walk probability of landing on the node N starting from the query concepts within the domain graph G. So we do have two parameters, alpha and beta. It's a simplification, I know, please don't write to me, but there's another parameter. Yes, I know, I just want to be here on the main idea. So how is this fusion, how is this braiding kernel now operational? You understand that this is the core processor logic that we are talking about. It is not the sum of alpha and beta. No? We have to perform here a gated fusion operation to reject the hallucination and the irrelevant noise. You remember in the first part of the video I showed you that the hallucination is here now, is here, this big minus here in the grid. So we have a high individual score and zero collective support. Yeah? The hallucination is not supported by the research community or published upon. It is only apparent here in my individual score. And the irrelevant noise has here high collective scores, but zero individual relevance for me. So I don't care for something that is so far away, I don't even understand it. And now we calculate here the braided score as braid. And this is now defined, since you know the title of this video, by a geometric interaction term of two manifolds. So I told you, we're going to look here, and it is not a coincidence that I tried to make this here not as a vector, but more like a wave function. We are looking here at the interference pattern. So just going to give you the result. The braided score is calculated here with an alpha and a beta, and in this structure, where we have a linear mixture of alpha and beta. So what do I know and what does the community know? And a structural gate. And this structural gate is now really important. But you know, if you look at this and you think about the very first PDF archive that we just talked about, the MirrorMind, you understand, wait a minute. If this is now an interpretation here for the mixture process, I can use this imagination, come back to the first PDF, and also build here the identical formula. And now I say here, the braided S for the MirrorMind is an example like this. Have a look at this. So you see, those papers not only have a very similar topic, but given here the mathematical formula of the first paper, of the second paper, I can induce now an equilibrium, an almost identical idea where I can come up now with the braided score for the MirrorMind. And you see, they are operating now differently. Why? Because this has a repulsory effect, the first one, and this has a structural gate. So there is a difference, but they are otherwise real similar. So what is the critical nuance that distinguishes this? No? I told you MirrorMind is for the scientific discovery process here, and the PersonaAgent here is, of course, about a recommendation. While both systems use here the braiding mechanism, they use here the individual stream alpha for opposite purposes. One is repulsion, and this is here in MirrorMind. The individual stream acts as a negative constraint. Remember, this was the deep blue gravity well, where I told you, this is what I know best. This is where I'm sitting. I'm lazy. I don't move at all out of my beauty zone here. And I need now some power, some impetus to move me out of there for the optimal path to P star. So this is now in MirrorMind a repulsor, my alpha. Now, of course, in this, again, here, this is here the term, our novelty repulsor, if you want to be specific. So you do have an intersection of a high domain visibility and a high persona surprise. And the optimization objective is to find now the node N that maximizes this S braided value for, in this formulation here, for the MirrorMind. Again, alpha, the individual inertia, measures how similar the idea is to what I have already written in the last 5 years. And beta is here the collective validity, all the global publication here, that is what is mathematically possible, that has been peer-reviewed, that has been agreed upon. Yeah, this is a real interesting research topic. This is here the wireframe grid that I showed you here in the first visualization here of this video. And we want this to be high because this is now exactly at the intersection that we're going to optimize. Now, of course, as I told you, I already showed you here the title in a particular way. If you read these two preprints in this sequence, and I'm just here sorting this out for you that you have an easier learning process, I can come up with this idea. So to those persons who are really checking here, whatever I tell you, is this really written down in the PDF? No. I'm now going beyond both PDF publications. I now combine them. Since they were published on the same day, the authors had no idea from each other. But I now, reading those, I see they have common ground. And so let's do this. So my idea, careful, buckle up, is we can combine PDF1, MirrorMind with the PersonaAgent to get a unified contextualization and output. So, image 1, clear. Now we have P star, the proposed great new idea where I have to go. And now all I say is, listen, if I have now this idea, I can bring it over now into the PersonaAgent where I told you we work now purely in a graph structure, the GraphRAG structure for the PersonaAgent. And I just bring this over as one node for the network. This is it. I mean, simple, come on. This is all you have to do to have some new insights. And I'm trying now at the weekend to combine both coding and, Gemini 3 Pro will do the coding for me. And maybe I can build this system operationally. Let's see. But of course I can insert any node if I want. And why not insert here the perfect research idea node here into the interaction node here of my personal history, because this would be my personal future, the very near future where this system tells me, hey, integrate this into your graph, knowledge graph, because this is your future that you should research. And then I just combine this here with the PersonaAgent as published already with the concept nodes, with the community nodes. Here we have the braiding machine that does here our braiding processing as I already described to you. And then the output, what we have is a linearization. A linearization context window where I showed you I have the perfect system prompt for me as a persona, for me to be an intellectual sparring partner. I have my personal history that I present here to the AI, the collective signal, what has the AI community done in the last 5 years for my particular brand new idea. And then I get now a refined contextual linear idea. This is here the P star and the collective insight here, also from a purely graph structure. So, you see, just braided together, everything together, and isn't this looking gorgeous? Now, if you want to go a little bit deeper, I further annotated this graph that was built with Nano Banana Pro. So here you find some additional sorts here from my side, but yeah, I'm sure you get here the idea. So this image now illustrates here a new solution to the cognitive flatness. We want to solve this, no? And we sequentially apply here two simple structural operations. We have an optimization, as I showed you in MirrorMind. So we find a local maximum for novelty within the validity constraints. This is here our blue graph. And the contextualization as the second structural operation, as I've shown you today, authors of PersonaAgent did. So what they did, we anchored the maximum in a heterogeneous knowledge graph to ensure it aligns with both the personal history and the social reality of the research community. Take a step back and think about what we have just achieved just reading two papers. You have read now only two papers. Structure is the new prompt. The intelligence itself is not here, because this is just the input to the LLM. This is not. The intelligence is encoded in the manifold and in the graph, while the LLM serves merely here as a transversal engine that is now computing this. It is not even computing this, because this manifold and the graph are constructing constraints on the operational space of the LLM itself. So what I want to propose to you that this shift here defines the next generation of neurosymbolic AI. Why? Because the locus, the place of intelligence, is shifting now from the parametric knowledge of the LLM, the model weights, the tensor weights itself of the vision language model, to the non-parametric structure, to the external architecture. So for my case, This would be here my intellectual landscape with the community landscape proposes here the path, my personal path to my personal optimal idea. And then I bring it here into a pure graph representation. I have here the braiding process, computing here this, and then I have here more or less all the history of mine and all the intelligence and the development of my scientific ideas here already presented here. No? So I think we are shifting here more away from the LLM as the only source of intelligence, and we have a lot more non-parametric structure that will do here in front of the LLM the real intelligence work, if you want to call it. No? Now, maybe you have seen that some days ago I posted here on my channel also here the latest research here from medical about manifold learning for medical EEG. And I've showed you here a publication. They discovered it really depends here on the mathematical space that we construct. And they found that the Euclidean latent spaces distorted the true structure of the electroencephalogram. They said, with this, this unconstrained vector space, this is not optimal. We can use AI for medical here because nearby neural state may be mapped for a path in this unconstrained vector space. Irrelevant state may become artificially close, what we do not want. The attention operates with the wrong metric operator, and the dynamics prediction must learn the geometry from scratch, which is unstable in itself. And the authors found a solution, and they said we have to build a Riemannian variational autoencoder that will fix this by forcing the complete latent space to have the correct curvature. It is just about the geometry of the space. And they say once we have fixed the geometry and put on constraint on this space, the geometry becomes correct, the geodesic distance becomes meaningful, the geometric attention works properly, and neural ordinary differential equation trajectories become smooth, consistent, and stable. And it is also this paper here that I already showed you here. And I've given you a very short introduction. What is a Riemann variational autoencoder? What is here the geometric transformer, in particular the geometric attention, how it is calculated, and why do we need manifold constrained neural ODEs? But have a look at this paper. This is here from Yale University, Lehigh University, Bethlehem, and School of Medicine, Yale University. And they already, and this is here just the day before, November 20th, 2025, and they did something similar, not the identical idea, but they also said, hey, listen, our solution space is too huge, it's too unconstrained, it doesn't make sense, no? We just don't waste energy and everything, but it's not stable, it is not what we need. And they built here this Riemannian variational autoencoder. Then they built here the geometric transformer. And you see here too, we operate here on a very particular manifold with a very particular optimization in a very particular positional encoding, if you want here, for a path optimization problem. And then we bring this path optimization problem from a manifold in a pure graph structure. We do the braiding and then we get a result. And this is more or less exactly here on a different complexity level what they did here with their architecture in this particular paper. And they called it a manifold former, the geometric deep learning for neural dynamics on Riemannian manifolds. And this is now my third paper that I want just to show you, because I have a feeling this is the way we're going with the complete AI system. It is not that we're gonna have the next extremely huge LLM and we put all of the intelligence only in this LLM. I think this would be the wrong way. I don't feel that this is the right way to go. But of course you could say, okay, this is now your idea, but let's increase the complexity. No? Because if we are playing around that we have now help in the visualization and I don't have to do this visualization by hand, I can now think a little bit longer, no? Like an AI that thinks a little bit long on a problem. So let's increase the complexity further. Yeah? So I found not only this third paper, but I found another paper, a really high-level paper, that it brings this to a complete new level, but it has a coherence in the development. But I think this is the end of part one. I think the video is already long enough, but I just wanted to present you some brand new ideas in AI that I have a feeling will be the future of AI. And I have to tell you, the next part will a little bit more challenging. So I decided to do part 2 of this video, and it will be only an expert outlook, and I will do it for members only, because I want to give back to the people to support me with their membership of my channel. So I want to give back to them, and I want to present them just my ideas and the way I see the future of AI. So I think part 1 provides already so many new ideas for the AI community in general. But if you decided here to support me personally, I want to give back to you, and therefore part 2 will show you here my personal thoughts here, and we will increase the complexity, and we will go a step further, and I will give you an outlook of AI. That is just what I feel that we're going to move together as an AI community. Anyway, I hope you enjoyed it. It was a little bit longer, the video, but I wanted to show you how amazing it can be if you just read 2, 3, 4, 5, maybe 100 new PDF papers, and you see common patterns. You develop here common ground. You see that everybody is moving in the same direction, and I just wanted to make it crystal clear to you where this is now going to be. But of course, it could be that we have a brand new development tomorrow, but at least let's have fun with AI. Let's play with it. It is so beautiful to discover here complete new ideas in artificial intelligence. So I hope you enjoyed it. Maybe you want to subscribe. Maybe you even become a member of the channel. Anyway, I hope I see you in one of my next videos.